In this lesson, I cover fault handling and the fault module. You might view this module as the base software for this course. It handles faults in general, regardless of where or how they were detected. Now, the Stack Overflow protection feature is implemented in this fault module, but that's a big topic and I cover it in its own lesson. And I cover writing to Flash in this lesson, even though it's in its own software module. It's not a core topic, and I don't cover it in great detail. So there's a lot of material in this lesson, and it gets pretty hairy here and there. I find this kind of stuff challenging and rewarding, and I hope you will also. So let me quickly go through an outline of this lesson. I start with the requirements of what we want it to do. Then I go through a number of design topics and describe how the MCU itself deals with faults. Then I talk about writing to Flash, since we save fault data to Flash. Then I go through the Flash module API and implementation, and then the fault module API and implementation. Then I do a demo where we force a fault and then analyze it. And finally, there are some prompts or questions for you to consider, and for each one I give you my take on it. So here are the requirements for the fault module. The following types of faults must be supported. For example, CPU detected faults such as use of an invalid pointer, one that doesn't point to any hardware, invalid memory operation, for example, writing to read-only memory, and this includes stack overflow into a read-only stack guard area. Things like integer divide by zero, illegal instruction. And then other faults that are not directly detected by the CPU would be watchdog trigger and faults detected by the application software, such as some very serious data structure corruption, and it decides it can't go on. So upon the fault detection, write the following info, which I refer to as fault data, to Flash and to the console. The type of fault, the program counter and stack pointer at the time of fault, if possible, selected CPU registers and system registers containing fault information. The ARM architecture defines these system records or system registers. And then the lightweight log buffer. And if you're lucky, that lightweight log buffer will show some very useful information about what was happening before the fault occurred. So if the Flash already contains a fault recording, do not overwrite it, but still write the fault data to the console. And the idea here is if you're in sort of a continuous reboot scenario, you don't want to just keep writing that page of Flash again and again, or you could wear it out. So after writing the fault data, there's nothing more to do, so reset the MCU. Now, this might imply we're doing an automatic recovery kind of thing versus fail-safe, but it really depends on what the system does after it restarts. In other words, does it go right back into operation, or does it just sit there and wait for something to happen? And then finally, the fault data is written in a raw sort of binary format, and you don't want to decode that by hand. So there's a requirement to provide an offline formatting tool to make the fault data easy to read, and we'll be using this tool throughout the course. I'd like to say a little about MCU Reset, since we generate resets from the fault module. Typically, the reset pin on an MCU is both an input and an output. This is accomplished using a hardware technique called open drain or open collector, and the details really aren't important. So the pin acts as an input when an external entity is resetting the MCU, for example, the reset button. And the pin acts as an output when the MCU generates a reset, which is what we do in the fault module. So in this case, the MCU is telling the hardware that I'm doing a reset. Now, the key to this is that an MCU-initiated reset can reset external hardware. And this can be very important and can be a factor in selecting hardware. So if we go down here, here's the reset line or signal. Here is the MCU. It has what's called a pull-up resistor on this signal, and that's just a hardware detail. And here we have the reset button, and when we press this, it causes a reset on this signal. That's then an input to the MCU, causes the MCU to reset. It's actually an input to these other two devices as well. So here we have two devices that are connected to the reset line. One is a temperature humidity sensor, and the other is an I/O expander. Both have I2C interfaces. Now, the reset signal on these might be critical. For example, in the case of this I/O expander, you want to be certain that when a reset occurs, that these outputs all go off. The other reason that these reset inputs can be important is that devices, especially more complex devices, can get stuck and stop working. And the only reasonable way to get them going again is through this reset signal. I've seen this happen. If you look at my I2C course, you'll see a demo of a device that I do something to get it stuck, and it requires a hardware reset to get out of it. The last box I show is a voltage supervisor. What it does is monitors the system voltage, and it holds the system in reset unless the power is good. And this is normally when you first apply power to a system, although it also occurs when the system is going down and losing power. So MCUs can also do this on their own, but maybe not quite as well as a voltage supervisor. And so they're sometimes used when there's a particular need for it. So here are some design notes. So fault handling is performed in what we call panic mode. And generally panic mode is used when the system is in a bad state and you really can't trust anything to work. Normally you are headed towards a reset. So you tend to work at a very simple, primitive level, and you don't worry a lot about efficiency. So in panic mode, we disable the interrupts. We reset the stack pointer to the top of RAM to ensure we have a good stack. And we use polling, not interrupts or DMA, for all hardware operations. For example, writing to UART and Flash. Now, in case fault handling gets stuck, the hardware watchdog should reset the MCU. So that's sort of our backup. So we talked about in the requirements about the fault data. And so we have to put that in some kind of format. And so, first of all, the data is written to Flash in binary format, and it's written to the console in hexadecimal text format. The data is organized in sections, where each section starts with a magic number and a length. And the magic number tells the formatting tool what kind of data is in there. And the sections for a fault are, the first one is the generic fault data, including fault type, register values, and so forth. Then there's a section that contains the lightweight log buffer. And then there's a section which is just an end marker. There's really no data in it. But it tells you that you have the complete set of data. The fault data section sizes must be a multiple of the minimum Flash write size. That's a restriction put on by the Flash, and it's typically 8 or 16 bytes. So here's a simple diagram of the fault data block. And just as I stated, it's broken into 3 segments, one for general fault data, one for the lightweight log buffer, and then an end marker. And within each segment, it starts with a magic number and a section length, and then followed by data. And that's all there is to it. Now I want to talk about exception processing. Now this discussion is specific to the ARM Cortex M4 MCUs, which use the ARM v7-M architecture. And down here at the bottom I have a reference, an ARM document, where you can find this information. The version of the document I used here is in the GitHub repo called ram-class-1-materials that I mentioned in the introductory video, or you can just go to the ARM site and get the latest version of it. So exception processing starts when a fault is detected or an interrupt occurs, and then the address of the handler code is found in the vector table. So I have 2 tables here that I snipped from the architecture reference manual. This table B1-4 on the left lists the exceptions, which are either faults or interrupts, and it gives their exception number. And over here, table B1-5 on the top describes the layout of the vector table. And basically, the exception number is used as an index into the vector table to get the handler address. Now, index 0 is a special case for the stack pointer. So the exceptions of greatest interest are those due to faults detected by the CPU listed here. And these are the things discussed in the requirements, and they were discussed in more general terms. Also of interest are exceptions we never expect. For example, interrupts from devices like a UART or an SPI that we are not using. Even though we don't think they will ever occur, we should be prepared just in case, and there's really no extra work to do this. So the initial handler, which is found via the vector table, needs to collect critical information and then call or jump to a secondary handler that's actually in the fault module. So for our MCU, the initial exception handler is coded in assembly. So we will write a tiny amount of assembly code, really as little as possible, because we want to do as much work as possible in C. So the secondary handler in C, in the fault module, continues to collect information, and it ultimately generates a fault data report as described in the requirements, and then it resets the MCU. On this slide, I have a little more information about what happens in exception processing regarding the stack. The reason is we will want to collect this information for the fault report. So we have this figure B1-3, again from the ARM Architecture Reference Manual, and it shows how key state information is saved on the stack when an exception occurs. Now these two stacks here are for the two cases of whether the stack pointer was on a 4 or an 8 byte boundary. For reasons I don't know, the exception stack information must be on an 8 byte boundary. So in this case on the left, an extra word was added to achieve that. So we can see what is saved. First, some general purpose registers, and then the link register, which is also R14. Then the return address of where we were executing when the exception occurred, and then a processor status register. Now, if you look in the reference manual, you'll see that if there is an FPU, floating point unit, and it's active, then the floating point registers will be pushed on the stack as well, and they'll be up here. But the fault handler is only collecting information starting at R0 going through the processor status register. So we don't really have to worry about whether this padding word is here or whether there are floating point registers up here, because we will be using the new stack pointer, and we'll be addressing relative to that, and we'll only be going up to this point. Here I have a few notes about writing to Flash. Now this topic is sort of outside the main scope of this course, so I don't want to spend too much time on it, but we do write to Flash, so I need to cover it. And the Flash code is put in its own module, in case I ever want to use it for something else. So I want to point out as well that this discussion is specific to the STM32 MCUs I have worked with. So typically, to write to Flash, you have to first erase it. It's not like RAM where you can just overwrite a value. Typically, you can only erase Flash in chunks, referred to sometimes as a page, sometimes as a section or a block. Sometimes all the pages of Flash in the MCU are the same size, and sometimes they're different sizes. For the MCU, we are using their different sizes. You might also be able to erase all the Flash in one operation. We don't do that, but just wanted to point that out. Now, when you write to this erased Flash, it generally must be on some even boundary. For example, the address must be a multiple of 8 or 16, and the amount of data must be a multiple of 8 or 16 bytes, for example. So we need to reserve a page of Flash for fault data. So we're using the GCC toolchain, which is used by our IDE, and the code and data are mapped to Flash in the linker script. Now, one easy solution to choosing a page is just to use the last page of Flash. And as long as your code isn't using all pages of Flash, this is simple. However, for the MCU we're using, this one, the pages of Flash are of variable sizes, and the ones at the end are very large. So I don't want to reserve that last page because it's big. So what I do instead is I take the second page of Flash after the vector table and reserve it for fault data because that page is much smaller. Now this does require some editing of the linker script, and we'll see that. Here we are in the Flash header file, and I just want to show you the simple API for this. So this is the start function, which is just a standard module function for startup. And then there are just two APIs. One is to erase a page, and one is to write data. And notice the word panic is in these API names. That's because they are used in panic mode, which means they block, they don't use interrupts, they do polling. Here we are in the implementation file for Flash. I'll go through this very briefly. So first we're going to look at the function that erases a page of Flash. So here it is. And I'm not going to, if you look at the reference manual, it gives you sort of step-by-step instructions of how to do an erase and then how to do a write. And so that's pretty much what this code follows. There are not LL API functions for this, so I'm referencing the registers directly. Fortunately, there are symbols defined for all the registers, so I don't have to do that myself. So it's writing to, I believe this is called a control register, and it's just writing bits based on the instructions. And you can see that there's these ifs because it's done slightly differently for different MCUs. And after we get it all set up, then this is common code that actually starts the erase. And then we sit in a while loop waiting for the erase to finish. And we're looking here at a status register. And then there is this function, I won't go through it, it just does some common cleanup, and that's pretty much it. So the next thing is the write function. It's the same thing. Look in the reference manual. It gives you more or less step-by-step instructions, and you write these registers and set them up as it asks you to do. And here is the actual loop where it writes the data. So there's that. And every time it writes a chunk of data, it has to wait for it to finish. And then when it's all finished, again, it calls this function which does some cleanup. And that's it. Now we're in the linker script, and I wanted to show you how I reserve space for the fault data in Flash. I would have liked to put the fault data in the last page of Flash, as I did in other MCUs, but in this MCU, the pages at the end of Flash are quite large, while the pages at the beginning of Flash are smaller. And I didn't want to use one of those large pages and waste a lot of Flash. So this makes it a little bit more difficult, but it's not too bad. So first, this has changed quite a bit. It used to just have RAM and Flash. I created these two new sections, and I modified the Flash section. So this first section is where the vector table goes. It has to be at the beginning, and so it's one page, it's 16K of memory. Following that is the fault data, and it's also one page, 16K. Following that is the redefined Flash area, which starts after the fault data. It used to be 512K. If you add all these three, you get 512K. Now it's 480K. So that's one change I had to make. And then in these sections where we assign code and data, I had to pull out the vector table on its own. And so that gets assigned to this new ISR vector area. And nothing gets assigned to the fault data area because that's handled programmatically from the software. And then everything else, as normal, goes into the flash area, which is now a little bit smaller. So that's how it was done. Not too bad. Here we are in the fault module header file, and I'll just briefly show you the API. So the first thing I want to point out is this enumeration, which is the fault type, and we currently just have two, watchdog and exception. In terms of the function APIs, these two are standard module APIs. I call them part of the core API, and they're just used during system initialization. And then these remaining APIs are specific to the fault module. So this first one here, fault detected, can be called by any code to say I have detected a fault. And it passes the type of fault and some parameter. And the fault module will collect some information, generate a fault report, and then reset the MCU. So this function never returns. This function is somewhat similar, but it's specific to exceptions. When a fault or unexpected interrupt exception occurs, first there is an initial handler that's written in assembly, and that handler will very quickly call this C function. And it passes it the stack pointer at the time of the exception. So again, this handler generates the fault report and so forth, collects information, and then it resets the MCU, so it will never return. So here we are in the fault implementation file. So the first thing I want to look at is a data structure. And this is the fault data. And so this is the magic that begins all these data segments. And then here's the fault type and the parameter. And this is all the data that we collect about the fault. This will ultimately be written to Flash and the console. And we'll be looking at code that fills this structure in. So now we're going to look at the fault handlers. And the first one is here. Now this is for faults that are not exceptions. So an example would be a watchdog triggers, and this will get called. So we go into panic mode, and we disable the MPU, which is just a precaution. And now we're going to start collecting the fault data and put it in that fault data structure. And that's what this is doing. And then we call a common fault handler, and we'll look at that in a little bit. So this is the other type of fault. This is when we get an exception. And if you'll remember, when an exception occurs, some information gets pushed onto the stack, and we want to save that information in the fault data if we can. So here is the entry point, and notice the stack pointer at the time of the exception is passed in. We again go into panic mode. We start to collect fault data, and then here's where we want to get that data that was pushed onto the stack when the exception occurred. Before we do that, we have to take a good look at that stack pointer that was passed in, make sure it's valid, it's pointing into the stack and so forth. If everything is okay, then we do a mem copy of that information off of the stack for the exception, and we copy that into the fault data structure. And then once again we call the common handler. So here is the common handler, and it fills in even more of that fault data, including all of these system registers that are useful in the fault case. It gives additional detail. So now we have that fault data structure filled out, and we can record it. And so we have this function called record fault data. We'll look at that in just a minute. After that's done, we record the LWL buffer, and there's an API to get the address and length of the LWL buffer so it can record that. And then there's that end marker, which is just that tiny little section at the end. And when all of the recording is done, we call this function which resets the MCU, and that's the end of it. So let's look at the record fault data. And there's two sections. One is to write the data to flash, and the other section is to write it to the console. Now the flash has that special requirement that says if there's already fault data there, don't overwrite it. And what it does in this line here, it's looking into the flash, and it's basically looking to see if that magic number is there. If that magic number is there, that means there's fault data there. Don't write anything. If it should write something, then this do flash will be true. And then if the data offset is 0, it means we're just starting. It erases the page, which is right here. And then after that, it writes the data. So that's it. Now here's the console. The console is simpler because it's just doing basically printing the data out as hexadecimal, and that's not too tricky. So the last thing I want to show you is a console command called fault test, and we'll be using this in some of the demos. The one I want to look at here is bad pointer, and let's see what bad pointer does. If you enter from the console fault test pointer, it will get to this point. Here's where it detects that operation. And so what it does is it takes this value, all F's, it casts that to a pointer to an unsigned 32, and then it tries to write to that location. There's no way that's going to work. That's going to generate a fault. So that's it for the fault module. Here I am in the assembly language file that has the vector table and the startup code. And here's where I modified an exception handler to call the C function in the fault module. So I need to look for the label default underscore handler, and here it is. And this handler is used for all exceptions that don't have specific handlers, and this is actually nearly everything. The only exceptions that have handlers are mainly interrupts for the peripherals we're using, like UARTs. So by default, the default handler, this is the code. It just branches to itself in an infinite loop. So what I replaced it with are these three instructions. So the first instruction takes the current value of the stack pointer and moves it into R0. And when you call a function, R0 is the first argument. Then I reset the stack pointer, as is done on initialization, to be the highest value in RAM. So now we know we have a good stack. And then I just simply branch to that C function in the fault module. And that's all there is to it. Now for the demo. We're going to do the bad pointer test and analyze the result. So here I am in the console, and I'm going to reset the system, pushing the black button. And we're getting that logging again from the temp hum module. So I'm going to enter Control L, which stops that. And now I'm just going to do the fault test pointer. And the system just reset, and I'm going to stop logging again. So what happened when we entered that, as you know, it did something bad, and here is where it dumped out the fault data to the console. And we're going to grab that, and we're going to put it in a file so we can use the formatting tool. So here I'm in the fault directory in the source code tree, and this directory just has the fault.c file and the formatting tool, which is called logformat.py. It's a Python program. I'm not going to look at the implementation of this. You can take a look if you want. Now, to run this tool, you first have to put the fault data in a file, and I've done that and called the file raw .text. So let's just cat that, and that's what came out when the fault occurred. And so now we're going to run the tool, and to do that you have to tell it where the source code is, because it needs, this is for the LWL stuff, it needs to find those LWL statements in the source code in order to decode it. So if I just point to the parent directory, it will be able to find all the code from there. And then you need to tell it where your raw text is, and I'll tell it that. And there you saw the formatted text fly by. Now I'm going to do this again, but I'm going to put it in a file that we can look at in an editor called decode1.txt. And so there we are. So here's the decoded data. So the first thing we see in here is the fault type. Now this is that enum in fault.h, and this means it was an exception. The fault parameter is the exception number, and 3 is hard fault. Then this is the data that was taken off of the exception stack. And here's sort of an interesting thing. Register 2 contained the value bad, which is what we were trying to write. What would be most interesting in this is this return address, this 800C974. I expect that will be in that fault test command for bad. This would be in that line of code where it's setting, doing that bad address and trying to write to it. So we have also the stack pointer at the time of the fault. This link register, this is like a return address. This gets into ARM, how ARM works, and I won't go into that right now. And so, and then there's these additional fault registers here. So after that, we see the LWL trace. This skipped data at the beginning. What this means is I don't think we've actually filled up the circular buffer by the time the fault occurred, because I did a reset and we don't have a lot of trace going in here right now, just these ticks and these temperature humidity measurements. So it didn't get full. And of course in this case, if we go to the end, so this is the last trace before the exception. There's nothing interesting in here, mainly because we haven't put much interesting stuff in the logging. In a real application, presumably there'd be a lot more things in here. By the way, this we do print the uptime, and it had been running for 16 seconds when the fault occurred. So this gives you an idea. So if this was a real problem, let's say in the field or in the lab or something, you would be going through this data, I can tell you, in great detail and looking at all this and trying to figure out what happened. I want to show you a few things about flash storage here of fault data. So I'm at the console, and there is a fault data command that will dump out the fault data from flash. And there it is. So we could take this data, cut and paste it, and decode it just like we did with the data from the console. It's the same data. So as you know, there's a requirement that says if there is already flash data in there, don't overwrite it. So let's say you have a fault, you get this data, and you've analyzed it, and now you want to make sure that the next fault gets captured. And so how would you do that? Well, there is a fault data erase option. So if I do fault data erase, that happened, and then you might wonder, well, what does the data look like now? And it's all F's. That's typically what flash looks like when it's been erased. So that's how you manage the flash with this simple console commands. So here are the prompts or questions for this lesson. I'll just pause here for a second and then go through them one by one and give you my take. How might you store multiple fault data dumps onto flash? Well, if the reserved flash page or pages can hold multiple instances of the fault data, then as faults occur, the fault data can be written one after another in Flash. For example, the MCU I was using, I believe the page was 16K, and I think I could store a number of fault data dumps in that area. The logic to erase the page would be a little bit more complicated, but I don't think it would be that bad. And if you do have lots of flash, you could, of course, reserve multiple pages. You could reserve all of the extra flash maybe for fault data dumps. Assuming you can't get good stack backtrace within your MCU software for fault reporting, can you think of some alternative? And the issue here is that with ARM, because of how ARM uses a stack, it is difficult to get stack backtraces. Well, here's an idea I have. I don't know how well it would work, but we expect that the stack will contain return addresses for functions. They will be there. You could search backwards in the stack for values that are valid flash addresses and potentially return addresses. And you might save the first 10 or so of these values that you find in the fault data. So then the offline formatting tool could automatically convert these addresses to function names and line numbers. And then if you had that, you could look at that and you might be able to work out the backtrace manually. If you had storage where you could save the entire RAM image after a fault, how might you analyze it? And I have a hint here. What is the equivalent for a Linux process? Well, regarding that hint, in Linux, when a process crashes, it can leave a core dump file which contains the RAM image. Debuggers like GDB allow you to use the core dump to do an offline analysis of the dead process at the source code level, looking at variables and so forth. A similar thing could be done with RAM image dumps for MCUs. And I actually implemented something like this quite a while ago on an embedded system, a rather large embedded system. And once I had that working, that was invaluable. It really made working on crashes much, much easier. Is resetting the stack pointer to its initial value, the highest address in RAM, in the fault handler too drastic? What are alternatives? Well, doing that is simple and it's safe, but maybe it is too drastic. I really wasn't that worried that we would overwrite part of the stack when we're doing this, but we don't really have to do it in all cases. So an alternative is to check the current stack pointer in the fault handler and check if there is sufficient remaining stack to process the fault. If so, just leave the stack pointer alone. Another alternative is to reserve some RAM for the stack for fault handling, and this assumes you have RAM to spare. In this case, you use that memory for the stack and you completely stay clear of using the normal stack. You just don't touch it. So this is the end of the fault module lesson. I hope it was useful for you, and thanks for watching.